Hi guys, welcome back. So last video we had done an analysis for a beam under flexural loading and we were expecting somewhere around 3000 megapascal as from our calculations. But just for your information, 3000 megapascal is definitely way beyond the material yield strength for steel, which is about to be 200 megapascal. So this is definitely not a practical value, but this is for understanding and how we can do analysis in Abaqus for such kind of a problem. Now, this video we are going to see what will be the stress levels if we do rather than a beam element, if we go and use for solid elements. So let's quickly go for modeling. So we'll make another model here itself. This is another way of creating two models in one particular CI file. We'll go create model 2. Let's call it model 2. Here a couple of things if you are doing for thermal analysis and all those things. These things might be required. Interesting thing, you can read data from the another jobs as well. We're not going into those details. So model 2, what kind of part we want to make? First, let's go here in part module. We are going to go for a 3D solid element, so we'll use 3D modeling space and solid shape extrusion. Let's go for extrusion. Our part dimensions were 100 cross 100 mm and 500 cross 500 mm length. Just fix one end. 100 mm, 100 mm width. Cross section is ready. It's ready for extrusion now. How much length? 500 mm blind. Okay, so model is ready. Next thing, property. We'll be making another uh, macro in the next video to avoid all this repetitive task elastic, and I'll be going for in future videos we'll talk about composite modeling as well. 0.28 dismiss. Now material is there, we have to create a section of solid. Remember last time when we were doing beam analysis and all, we were using beam, and under that if you are using a bar kind of or truss kind of problem, then you will go for truss, and if it is a beam then beam, but this time solid. So this is the segregation here. If you use shell elements and also, then you'll go for shell. We'll look for that as well. I'll make another video for that. And difference of solid shell, we'll look at those things. Under shell itself you'll be have a conventional continuum stack shell and all those things. Anyway, so this video will see create section, steel section. Yes, steel, please choose steel. Now section is we have to assign it. Let's quickly assign the section to our part. You can either choose to create a set or not. I'm just avoiding it to avoid my space. Steel section, yes. Color is changed to green. Super. Material is assigned. Let's quickly mesh this particular part. Okay, here one thing I want you to observe is this green color, parrot color. So this means your meshing will be structured meshing. If you don't do this, you can either get yellow color or you could get pink color. Pink color would mean you will get tetrahedral sort of meshing. If yellow color, okay, it could be combination. It could be structured or unstructured, something of that sort. It will be combination basically. Somewhere you will get tetra, somewhere you will get quad elements basically. Okay, let's have a look what kind of elements. 3D stress elements. Okay, Linear or quadratic, you can choose. We'll try to see with linear elements and see what happens. All right, mesh is done. Let's bring this part into assembly module quickly. Here, one thing you can note in assembly is when you bring a part or import a part, either you can choose it to be mesh uh, instance, to be independent or independent, something of that sort is there. We will talk that in future videos. Basically, what happens is if you are bringing a part from part module, I- the question is, do you want to import the mesh or not? So there are some cases where you might not want that. You want it to be independent, but we are using dependent itself. So whatever part meshing we have defined here in the part module, same mesh will be coming in the this module as well. Okay, let's we need to define a step. What kind of analysis we want to do? Static, yes. No linear geometry of, we are not going into those details again. Um, all right, so where do we want to apply the load? So the load we are applying is shear load. What we will do is we'll have a coupling over this particular surface with the point and apply the total load of 1000 kilonewton at that particular point again. The same technique we used in the bar analysis under tensile load. So for that, go to interaction module, and first of all you want to make a reference point. We'll use 50 comma 50. This is one of the reason I always fix the left hand corner so that we get the point where exactly we want on the surface, because otherwise there's a tendency your cross section can move in the sketch module at that time. Anyway, so we have the part our reference point ready. Let's quickly make a constraint. We'll make a coupling between what is the control point. This reference point is the control point. Done. Which surface you want this particular surface to be with respect to, let's call it structural coupling. You can see what all degrees of freedoms it has, restraint, and you can even choose weighing method. We'll keep it uniform. All right, so we have our point coupled with the surface. Next thing is to apply the loads. Quickly apply the loads. So most of the process which I'm following now is similar to whatever we have done so far in the previous analysis. It's just matter of which direction I'm applying the load and what kind of element I'm choosing. Select point for the loads. We have chosen this reference point. As per the global coordinate system, we want it to be in minus y. So this 1 means x, 2 means y, 3 means z. Minus y would be, let's see how much, minus 1000 kilonewton, right? 1000, 1, 2, 3, 6. So yeah, the load is applied in the bottom direction, right? So load is applied. Let's quickly go for boundary condition. We'll keep uncasted because we have been following the same thing so far. Uncaster. All right. So I think model is ready. So this one, the previous model, let's copy it. So we made this model in the model 2, right? Beam 1 solid model. Let's call it beam 1 solid. We'll see what exactly happens. Let's quickly put the submit version button. Before that, you want to do data check, you can go for it. I hope we didn't make any error. In the previous model, in which one is completed, let's open it and see what we had obtained. S11, we had stress in axial direction, basically 3000, somewhere around 3000 megapascal. What is the deflection here? Can we see the deflection? Deflection in second direction. Wow, 24 mm. We are talking about this end. You see? Okay, let's see. Our analysis is done. We'll quickly see what happened with our model 2 visualization. Okay, my bad. Should go to model 2 and job. It is completed. This is the solid one. Results. Okay, great. Here, let me show you one more thing. What you can do is when you have two different viewports open here, so you can do linking between these two. So whatever you want to choose in the viewport 2, same will be shown in the view 1 as well. Link viewport. Go to view, and under that viewport, link viewport, click on this one. So once it is linked, let's say you go for U, so it will showing the U in the both, right? Magnitude in 2 second direction. Yes. So if you look here at the numbers, and one more beautiful thing is we can change our um, section field output, not here, viewport, viewport annotation option. Under the legend, you go here, you can change the numbers to fixed, and also you can choose not to show this bounding box. Then you get very good style of these numbers, more informative. See, in the solid elements we have got 25 mm. It's quite similar to what we had obtained in the beam model. Let's have a look at the numbers. Stresses in here S11. Okay, one thing is you won't be able to see because S11 here means different. S11 in the beam model means in the axial direction of the beam. So let's not link it. Unlink. How do we do it? Unlink. You click it here. You'll be able to unlink. Let's in our 3D model we'll be looking at S33. See, so as expected, we should be getting the maximum stress at the fixed end, right? Because that is a fixed end where the all the load is reacting. And quite interestingly, here you can see because when the bending happens, so bottom will be under compression and the top will be under tensile load, right? So we can same observe the top is under tensile load, tensile stress, and bottom is having compressive stress because we had applied load in the bottom direction or minus y direction. But definitely the values are lesser as compared to your beam model. And one thing to observe, in beam you couldn't observe that particular 3D sort of feeling that top should be under tensile, bottom should be under compressive, but you get more realistic number here. For example, near to 3000 megapascal, your elements are more stiffer, these 8 noded elements. If you want to have more reality, then you will probably go for quadratic elements. But yeah, we got a pretty good idea what exactly is the major difference here. We can see more 3D sort of visualization here. Top is tensile, bottom is under compressive. I hope this gives little bit clarity, and thank you for attending this call.